Hey there, and welcome to another deep dive. Today, we're going to be diving into AI.
Sounds exciting.
Yeah, and I know you hear this everywhere these days, but
AI is kind of the buzzword. Yeah.
it really is. But we're not just looking at the hype, we're getting into, well, something I find even more interesting. The quest for making AI, well, deep learning specifically, more efficient.
Yeah, that's right. It's all well and good having these incredibly powerful models, like the one behind ChatGPT, for example. But if
Mhm.
they're only accessible to, big companies with tons of resources.
Exactly. It's like having a sports car that guzzles gas.
Yeah,
It's cool, but not very practical for everyday use.
exactly. And that's the thing with a lot of these current AI models. They're powerful, but man, they are resource hogs.
I mean, have you ever noticed, like, when you're on your phone using a really demanding app,
Oh, yeah, it heats up like crazy.
and the battery, forget about it.
Totally. That's actually a really good example of what we're talking about today. These big AI models, like the ones based on Transformers.
Transformers, like the robots.
Well, the name's kind of catchy. They're these super popular models, but they need a lot of computing power.
Okay, so big, powerful models, but they come with a cost. So how does this actually affect, the average person?
It all comes down to something called quadratic complexity.
Okay, now we're getting into the technical jargon.
It sounds way more complicated than it is, honestly. Basically, it means that as the amount of data you feed these models grows,
It takes way longer to process.
way, way longer. It's not a one-to-one thing. So you double the data, you might need 4 times the processing power or even more.
So even though these models are powerful, they become really impractical for a lot of uses because of this quadratic complexity thing.
Totally. And that's a huge problem, especially since we want AI to be able to handle even bigger and more complex stuff in the future, right?
So what's the solution? Are we stuck with these power-hungry AI models?
Not necessarily. There's something else. Remember RNNs?
RNNs, remind me, that stands for.
Recurrent neural networks. They were like all the rage before Transformers took over.
Oh, right. So they're making a comeback. It's like fashion, everything old is new again.
Exactly. And you know what? Just like those classic fashion trends, RNNs have some serious staying power.
Okay, I'm intrigued. Why are people looking at them again?
Well, unlike those power-hungry transformers, RNNs can handle more and more data much more efficiently.
More efficiently, meaning,
They scale linearly, which is like the holy grail in a way. Basically, if you double the data, you roughly double the processing time, much more manageable.
that makes sense. But if RNNs are so great, why did we ever stop using them?
There was a trade-off. While they're efficient in theory, in practice, the traditional RNNs could be slow, a pain to train.
Ah, so there's always a catch.
Always a catch. But that's where this really cool research comes in. They've taken these RNNs and stripped them down.
Stripped them down.
Yeah, like getting rid of all the unnecessary stuff, creating something called minimal RNNs.
Minimal RNNs. Okay, so less is more.
Exactly. And the results are pretty amazing. We're talking hundreds of times faster than those old RNNs. And get this,
Faster, but do they work as well?
they actually rival, even outperform those fancier models on some tasks.
Now that's an aha moment. But how did they actually test these minimal RNNs?
They tested them on a bunch of tasks, one of them being this thing called selective copying.
Selective copying. Is that allowed? What is that?
Yeah, so imagine you're trying to have a conversation at like a really loud party.
Oh, I know the feeling. You can barely hear yourself think.
Right. You have to like really focus on the person you're talking to and try to block out all the other noise. That's kind of what selective copying is for AI.
So it's like picking out the important information from a jumbled mess.
Exactly. It's like finding a needle in a haystack. And these minimal RNNs, they're surprisingly good at it.
Really? Even better than the bulkier models.
In some cases, yeah. They were either right on par or even surpassed them in accuracy.
Wow, so not only are they faster, more efficient, they're also really good at this selective copying thing. What else did they test them on?
They also looked at how these minimal RNNs do in robotics.
Robotics. Okay, now that's just cool.
Yeah.
Are we talking like self-driving cars, that kind of thing?
It's all connected. One of the really tricky things in robotics is getting robots to learn complex movements.
Yeah, you see those videos like picking up an object. It seems so simple, but
It's deceptively hard. But that's where minimal RNNs could be huge. Their efficiency means robots can process information, learn new skills way faster.
so robots that can learn and adapt in real time.
It's not sci-fi anymore. This could be the key to robots that are more adaptable, more useful, and in the real world.
Okay, now that's what I'm talking about. This is getting me excited. But We can't forget about language modeling, right? That's a big one.
Absolutely. I mean, that's how AI understands and generates human language. Think chatbots, even just text prediction on your phone.
So basically everything we use daily.
Pretty much. And if we can make those models more efficient, imagine how much smoother those interactions would be, right?
No more chatbot frustrations. They'll actually get what we're saying.
Exactly. And minimal RNNs, they could be a big part of that. They can handle those massive amounts of data you need for language modeling really well.
Okay, so this is all amazing, but I gotta ask, if these minimal RNNs are so great, why isn't everyone already using them? What's the catch?
Well, remember we were talking about those traditional RNNs, how they could be a pain to train?
Yeah, that was the trade-off, right?
Exactly. And while these minimal RNNs are way better, there are still some limits. They might not be the best for absolutely every single AI task out there.
So it's like having different tools in a toolbox. You wouldn't use a hammer for everything.
Perfect analogy. And that's what's so cool about AI research. It's all about pushing the boundaries, finding the best approach for each problem.
Makes sense, makes sense. But one thing that really strikes me about this is sometimes, going back to basics, keeping things simple, that's the best solution. And these minimal RNNs seem like a perfect example of that.
I agree. There's something elegant about their simplicity. It challenges that whole idea that we always need bigger, more complex models to get good results.
Right, it's like that saying, less is more. And speaking of great minds, this research reminded me of something Jürgen Schmidhuber, the AI pioneer. Yeah.
Oh, yeah, Schmidhuber. He's got some really interesting thoughts on this whole efficiency thing.
He does. So what does he have to say about this whole efficiency in AI thing?
Well, he sees it as more than just making things faster or cheaper. He thinks it's like a fundamental part of what it means to be intelligent.
Really? Okay, now you got to explain that one.
So Schmidhuber, he believed that intelligence, both human and artificial, is all about finding patterns and, get this, compressing information.
Impression, like zipping a file on my computer to make it smaller.
Exactly. But on a much bigger scale, he's saying the universe itself runs on patterns. And when we find those patterns, we're basically compressing information.
So the more efficiently we can compress information, the more intelligent we are. Is that what he's saying?
That's the gist of it. And he believes AI can learn to do this, just like humans.
Wow. That is mind-blowing. So where do our minimal RNNs fit into all of this?
Well, remember how we talked about them being designed to process information so efficiently?
Right, they're like the minimalists of the AI world, cutting out all the unnecessary stuff.
Exactly. And Schmidhuber thinks that this focus on efficiency is a big step towards building AI that can truly learn and understand.
So it's not just about speed or cost. It's about making AI more intelligent, more like us, in a way.
Precisely. That's what makes this research so exciting. We're not just talking about small improvements. We're talking about getting closer to the core of what intelligence really is.
This has been an incredible deep dive. I mean, we've covered so much, from the limits of transformers to RNNs making a comeback, and now this whole idea of compression and intelligence.
And we're not done yet. There's still a lot more to unpack.
Oh, I know. We've only scratched the surface. But for now, we need to take a quick break. But don't worry, we're not done with this deep dive yet. There's still a lot more to uncover.
Yeah, we're just getting started. Remember those acronyms, GRUs and LSTMs?
Vaguely, those are types of RNNs, right?
Exactly. GRU stands for Gated Recurrent Unit, and LSTM is Long Short-Term Memory. They're both super common RNN setups, and they both use these things called gates to kind of control how information flows through the network.
Okay, gates. Like a gate on a fence, controlling what goes in and out.
Perfect analogy. These gates and RNNs, they're like little gatekeepers, deciding which information is important, which should be kept, and which can be, tossed aside.
So how do they actually work, these gates?
Well, it gets a bit mathy, but basically they use these special functions to analyze the incoming data and figure out its importance.
And minimal RNNs, they have a different kind of gate system.
Exactly. The researchers, they found ways to make these gate mechanisms simpler, more efficient, without losing performance.
So they made the gatekeepers better at their jobs.
Exactly. Streamline the whole process, which makes the network way faster.
That's really clever. But making things simpler is often harder than it sounds. How did they actually do that with the gates?
They used some pretty neat mathematical tricks to cut down on how complex the calculations were.
Like what kind of tricks?
So, for example, they realized that some of the information these traditional RNNs were storing, it was redundant, like having the same file twice on your computer.
Oh, I hate it when that happens.
Right. So they found a way to get rid of that redundancy, which freed up a bunch of processing power.
So by cutting out those unnecessary calculations, the gates could work much faster.
Exactly. And that's just one of the cool things they did to make these minimal RNNs.
This is all fascinating stuff, but I gotta admit, I'm starting to feel like my brain's full, like I've been processing a lot of data.
It's a lot to take in, for sure. But hey, that's what makes these deep dives so fun, right?
It really is, and it just goes to show there's always more to learn, always new discoveries being made in AI.
Exactly. And who knows what the future holds? Maybe we'll be looking back at these minimal RNNs as the start of something even bigger.
It's an exciting time to be following this field, that's for sure.
Absolutely.
Well, on that note, I think it's time to wrap up this deep dive into the world of minimal RNNs and efficient deep learning.
It's been a blast exploring this with you.
To our listeners, thanks for joining us on this journey. And remember, the most elegant solutions are often the simplest ones. Until next time, keep those brains of yours curious and keep on exploring.
And don't forget, the future of AI is all about finding those elegant and efficient solutions inspired by, well, by intelligence itself.
Couldn't have said it better myself. That's a wrap on this episode of The Deep Dive. We'll catch you all next time.